Welcome back to physics. We are in the home stretch here. We're headed into the rest of magnetism, chapter 30, 31, and 32 that we'll all group together and pick kind of selectively from these topics and skip a few things to really streamline and focus on what's most important. So far in chapter 29, we've done a basic description of magnetic fields. We've looked at magnetic forces on moving charges, magnetic forces on current-carrying wires, and then when you make those current-carrying wires into a loop, the resulting torque on those, and some applications and things with mass spectrometers and particle accelerators. We're going to look now towards how we cause a magnetic field. So in the big picture with electric fields, we described them, and then we looked at what caused them, and we used two equations. Coulomb's law, which was kind of the workhorse, which would allow us to calculate any electric field. Sometimes the calculus was involved. And then we had the shortcut. We had Gauss's law, closed integral of E dot dA equals Q enclosed over epsilon naught. That was the kind of shortcut, but only worked in limited situations that were highly symmetrical. We're going to pick up the same idea here. We're going to go into Biot-Savart law, which is the workhorse, the kind of longer that always works way if you can crunch through the calculus. And then the sometimes works way when you have very symmetrical situations, which is Ampere's law. And then we'll move into other applications with induction and RL and LC circuits. So let's dive right in. We talked briefly about what causes magnetic fields at the beginning of chapter 29. And basically what we said were moving charges. So if we consider an atom, simple atom here, proton, neutron, electron orbiting around, you've got that electron moving, and in this case you have the electron spinning, and both of those motions can cause a magnetic field. Also, any motion of the proton, which is pretty limited, it can vibrate, it can spin. Usually if you have a magnetic field due to a proton, it's going to be more associated with a spin if that proton is in the nucleus. Now, considering the electron, it's rotating in orbit and it's spinning also. If you wrap your fingers in the direction of that spin or that orbit, they both happen to be going in the same direction, wrap your fingers of your right hand in that direction, your thumb points the direction of the magnetic field. Now, with that in mind, wonderful animation here, but the arrow is drawn backwards, that vertical arrow, because when you have an electron, you have to flip it over. Okay, so if we wrap our fingers in the direction of the motion, our thumb does point up on the right hand, but because it's an electron, not a positive charge, we would have to reverse it, and that magnetic field is actually going to be in a downward direction. We'll come back to that in just a second. So on our moving charge and our current carrying wire, right hand rule, if you point your thumb in the direction of the velocity, then your finger wraps the direction of the magnetic field. So your magnetic field, due to this moving charge, would come across the front and then wrap around the back. And I'll show you another picture in just a second. Same idea with a current. Remember, the direction that a current is denoted is the direction that positive charges would flow if they could. So if positive charges were flowing in the wire on the right, they would be moving up towards the top. So if you point your thumb of your right hand in the direction of that current and you wrap your fingers around, your fingers will wrap in front here and then behind the wire there. And so that magnetic field would actually spiral the wire. Here's another look at the right-hand rule and those directions. So magnetic fields that are produced are kind of unique because they are, from these different situations, spiraling fields. Here are different types of magnetic substances. This is basically just a little bit of terminology. Ferromagnetic substances, those are more or less iron-based substances, and they have a strong imbalance in the motion of the charges, resulting in those substances being very strongly magnetic. Paramagnetic substances, they are magnetic, but they're weakly magnetic due to the imbalance in motion. And typically these substances show no magnetic properties unless they are in an outside magnetic field. And when they're in an outside magnetic field, you will get those weak magnetic moments to line up. And so you will get a weak magnetic response from those substances. Diamagnetic substances, like copper, silver, and gold, you can induce a magnetic reaction, but it's a repulsion. So when you place these substances in a magnetic field, they will actually repel that magnetic field. So they will move away, they will set up a magnetic field that is in opposition to the one that set them up in the first place. Now, let's consider deriving magnetic field strength. And our first equation, Biot-Savart, and that's how it's pronounced, Bio for the first, whoever it was, last name, and Savart, the T is silent for the second one. Biot-Savart, that's the workhorse equation basically to be able to describe any magnetic field mathematically. So then if we start off with a simple wire, and I'm going to make this wire as general as possible. I'm going to make it kind of curved around. So this is a section of a solid wire, and we're going to put an electric current flowing in this wire, electric current flowing in that direction, and we want to ponder the magnetic field, say at a location somewhere here. I'll call that location P. If we think about that magnetic field, if we apply the right-hand rule and you point your thumb in the direction of I, then at P, your fingers will have gone into the screen at the below the wire and wrap back around at point P. So at point P, the magnetic field would be coming out of the screen at you. Now, Biot-Savart law basically describes how this field is calculated. So if we think about the field, the closer we are to the current carrying wire, it'd be logical to assume that it's stronger. The further away, the weaker. And so it will depend on the distance from that wire, which we'll call R. We can also get a stronger magnetic field if we adjust the current. I'm not going to derive the equation down, but rather I'm going to give it to you and kind of talk about the logic and then apply it. So your Biot-Savart law for the magnetic field at point P, B is equal to mu naught over 4 pi integral of I ds cross R unit vector over R squared. Couple of notes. R unit vector. It is a unit vector. Because it is a unit vector, it has a value equal to 1. So don't confuse that and say that's an R and try to divide it out with the R squared on the bottom. You cannot do that. It is just a pointer, and it allows you to be able to use the cross product and get a direction of the magnetic field. Mu naught. Mu naught is the permeability of free space. Now, what in the heck does that mean? Well, we had the permittivity of free space with electric fields, and that gave us, or an indication of the ability to set up an electric field in a vacuum, or it could be modified, like with the dielectric constant, for different substances. The permeability of free space is basically the counterpart for magnetic field. It is a constant that describes the ability to set up a magnetic field in a vacuum, and it will also be modified when we don't have a vacuum. So it has a value, 4 pi times 10 to the negative 7th, and the units are Tesla times meters divided by amps. So your Biot-Savart Law Equation, B is equal to mu naught over 4 pi, integral of I ds, cross r unit vector over r squared. Now let's specify these variables here. ds. Well, ds is a chunk of s, which would be a chunk of the length. So then if I spell out a little chunk of the length here, then ds, that's straight, would be a little chunk of that length. R unit vector. Well, if we spell out r is the distance from our chunk out to point P. So that would be R. So then our unit vector, I'm just trying to see how many colors I can possibly use. Our unit vector would be just a little vector of magnitude 1 that would point in that same direction. So then that cross product would be the angle between ds and r. So if I can, in the little bit of room I left right there, that would be angle theta. Now, I want to focus more on applying this equation. So let's consider a configuration of a current. We want to derive an expression down for the magnetic field at the center of an arc of central angle theta for a current carrying wire. The radius of curvature of the wire is r, and the current is I. So I'm going to draw. So there is our wire. I'm going to have the current traveling in it in a certain direction. Then our point in question, point P, would be out there at the center of the arc. So I'm going to draw a radius r there. So r and I, and then theta is also given. So same steps we followed on previous derivations. There's our base equation that we're going to start from, and we want to calculate what is the field at location P, specifying the variables. That's the second step in a derivation. So I'm going to go over to the diagram, and I'm going to chunk off a little ds, following in the same direction as the current would be. So we have our ds chunk. R, well, little r and big R are the same thing, so R is marked really as capital R there. Our unit vector would be along the same direction, so everything is marked. Moving back over to our integral, B is equal to mu naught over 4 pi. Now, considering what's inside the integral and what we can pull out, I has the same value across the entire wire, so I pulls out. Thinking about the 3 different sections, we have those 2 sections, and then we have the section in the middle. If you think about ds cross r, for these sections here where I'm marking a little ds chunk, ds would be in that direction, r would be in this direction. They are opposed to each other, which would be 180 degrees, and the cross product, purpose is to make things perpendicular. Cross product gives you a sine of theta. Sine of theta for those linear sections would be 0, and that would knock out the magnetic field. So then really we're focusing only on the arc, only on the section that I've highlighted in green. So then on that section, R is also constant, so I'm going to pull R out, and I'm going to write it as the constant, capital R squared. So then what's left in the integral, the ds cross r unit vector, the r unit vector is going to go away because it's only a 1. So then all I have is just sine of theta ds. Well, sine of theta, everywhere along here, yeah, I can't draw it on the diagram, 90 degrees. Your ds chunk is always perpendicular to your radius, so that's going to be sine of 90 degrees. So even that goes away. So all we end up with the integral is just the integral of ds. Well, we need endpoints of integration. So then our endpoints of integration for ds are basically going to go from no arc to all of the arc. So from 0 to s. So when we integrate, we get mu naught over 4 pi capital R squared s. S is equal to r times theta, which in this case that's capital R times theta. So when we put that in there, we get mu naught I r theta over 4 pi r squared. One of your r's divide out, and you get b is equal to mu naught I over 4 pi r times theta. Now, I pulled the theta out kind of separate because theta is the one thing that's changing. The other things are basically all set by the given situation. So if you are at the center of an arc, then that will allow you to calculate what your magnetic field is. Theta must be in radians. Let's consider what happens if this is a full circular loop. Mu naught I over 4 pi r theta. If this is a full circular loop, then what you have for theta would be the radian value of a full loop, which would be 2 pi, and you divide out and you get a mu naught I over 2 times r. So then generalizing our equation out, mu naught I over 2r allows us to be able to calculate what the magnetic field is at the center of a loop. Let's consider now a long straight wire. Well, a little bit on terminology. Long. What does that mean? Infinite. Now I know Bren's probably going to raise the question, well, you can't have an infinite wire. So what does that mean? Well, that means that the length of your wire is much, much greater than your distance from the wire. So if you have a 2-meter wire, you're a few millimeters, a few centimeters away. So your distance is reasonably close. So your wire approximates an infinite distance. So we have a diagram of the wire here. And what I want to do is kind of set this one up. But I'm not going to spend the time going through the derivation step by step, because we're going to focus more on what the results are. But I want to kind of develop the logic. So step 1, start with the equation. We identify what those variables are. So I need a ds chunk. We need an r. So then little unit vector r would be right here. ds cross r theta for that cross product would be right there. I am going to specify another quantity here, an x. Just looking at this, what we got there was a triangle with R and A. Thinking about moving across the wire and doing the integration, we're probably going to need to deal with chunks of the wire. And so we're going to need a value linearly across the wire. Now, I did use X there. Good decision, bad decision, I don't know, we'll see. But that would mean this ds that we just wrote would actually be more appropriately named a dx. That kind of sets up the variables. What I want to do now is move to the actual derivation. You can look at it. I'm going to talk through a few points, but but I'm not going to linger on the whole derivation, but rather the results of the derivation. So we have basically the same setup I just drew. In Biot-Savart law, I is constant, it pulls out. And then we need to think about, if we're going to evaluate this, what do we want to integrate with respect to? And we really have a few different options. We could integrate with respect to ds. We could integrate with respect to d theta. And we could integrate with respect to dr. Well, let's cross off the ones that are not terribly logical. If we think about integrating with respect to dr, we're not moving in the r direction, and that's a problem in terms of chunks. We're not moving from the wire up to point P, and so that one we're just going to toss out right off the bat. If we're integrating in terms of ds, it's an infinitely long wire. Well, then we're integrating from a negative infinity to a positive infinity. And that's going to cause problems in terms of values that we plug in. And so I'm going to cross that one off. If we think about theta, when we stretch out that dr chunk way to the left, theta is going to squeeze together. And when it squeezes together, it's going to start at approximately 0 degrees. When we shift past the middle, past A, and we shift way over to the right side, the value of theta is going to open up. I'm going to draw that because I can see it in my head, but I don't know if you can see it in your head. So when we come over here, R would be there. My dx chunk would be here, and theta is getting larger and larger. Well, as we approach a positive infinity, theta is going to approach 180 degrees, or pi. Well, sine or cosine integrating with respect to a theta, plugging in a 0 and a pi, those give us concrete numbers. They don't write us off to infinity. So then the best way to proceed on this one is to aim towards integrating with respect to theta. In that context, you're going to have to do substitutions. So over here on this side, there are some complex substitutions, but you can look through those and see how I plugged in. Your cosecants that you get divide out, and when all the dust settles, you end up integrating simply sine theta d theta. We get our endpoints there from 0 to pi, and we plug in values, and we get our overall equation down here. I'll color because coloring is fun. There's our equation. B is equal to mu naught I over 2 pi a, and this is a distance from a long straight wire. So then the question comes up, what if it's straight, but it's not infinitely long? What if it has discrete endpoints to it? Well, we can kind of pick up with the idea here and deal with that. If we go back to this step right here, in that step right there, if you think about it, if your wire had endpoints to it, all of the substitutions, all of the math up to that point would essentially stay the same. The only thing that would change would be these endpoints of integration. They wouldn't go from 0 to pi. They would go from a specific single value to a specific final value. And that will enable you to deal with different length wires just by generalizing kind of this step out and those endpoints of integration. Now, let's consider one example. Long straight wire carries a current I. A right angle bend is made in the middle of the wire. Determine the magnitude of the magnetic field at point P. B at P, basically what we can do is we can take this wire and we can separate it into 3 parts. You have the magnetic field for the top section, for the arc, and for the bottom section. Well, if we think about our different equations, okay, we've got our 2 equations there. The top section, it's not an infinitely long wire. It's a semi-infinite wire. Semi-infinite wire, if we think back on those endpoints of integration, we went from 0 to pi. Now those endpoints of integration would go from 0 to pi over 2. So I'm going to thumb back for a second. These endpoints of integration would go from 0 to pi over 2. So then our values of -1 minus 1 would just be cosine of pi over 2 is 0. Cosine of 0 is 1. Essentially, we would just get a value of 1 there. So with a 1 instead of a 2, then we maintain the 4 in the denominator. Or in other words, a semi-infinite wire gets a value for a field of half of an infinite wire. So then this is going to give us 1/2 of mu naught I over 2 pi, and your distance would be r. We'll worry about directions here in just a second. Your arc, mu naught I over 2 pi r, and then theta would be a quarter of a circle, a quarter of 2 pi. So that would be a pi over 2. And then our other side, that's going to be also a semi-infinite. Now let's think about directions. Right-hand rule. Top wire, if you point your thumb in the direction of the current, on your right hand, your fingers are going to wrap so that the field goes into the board down here and comes out of the board up there. On your arc, pointing your thumb would go this way, and then when you wrap, your fingers would come out over here, and then they would wrap into point P, so the field would go in. On our wire on the right side, your current is going in this direction, so when you point your thumb in that direction, the field would go in here and come out over there. In the location of point P, these are the directions that will apply for those three. They are all in the same direction, so these all have the same sign. So then we're going to get, so combining the terms and factoring out what is common, these two are going to combine to give us two of those. So then when we pull out what's common, we get a mu naught I over 4r times the quantity 2 over pi plus 1. In summary, Biot-Savart law always works. Sometimes it is complicated. Ampere's law, which we'll get to next, symmetrical situations. Instead of Gaussian surfaces, we're going to have Amperian loops, simpler to be able to apply. Really what I want you to focus on is understanding the basic idea of Biot-Savart law and then being able to apply the equations to get different magnetic fields. Ponder physics.